I'm Chandler Gillette.
I'm Alana Gonzales.
I'm Lindsay Pruitt.
I'm James Rowley.
I'm Paul Udorvich.
And I'm Christine Wiltbank, and we're Team 19024, Capacitive Volume Sensing, with our sponsor being Roche Tissue Diagnostics, Daniel O'Connor, and our mentor being Mark Brazier. Just a little bit of background, Roche Tissue Diagnostics HE600 is an automated slide staining system that processes approximately 200 slides per hour. The instrument contains 8 reagent reservoirs for dispensing appropriate reagents in precise volumes onto each slide. Roche was looking for a better system for measuring the volume of reagent in each reagent reservoir. The current system of float sensors are in direct contact with the reagents, susceptible to corrosion, and are expensive. In addition, the floats do not have a high resolution, measuring only 2 discrete levels. The Capacitive Volume Sensing project is a cost-effective and contactless solution to achieve a high resolution, precision, and accuracy volume measurement.
The system requirements were divided into 3 categories: performance, interface, and environmental. The performance requirements include precision, accuracy, and a resolution of 0.5 milliliters and 20 milliliters for the low and high regions respectively for all 8 reagents. The interface requirements include sample rate, digital output, analog resolution, refresh rate, and contactless measurement. The environmental requirements include temperature, vibration, and installation.
In designing our system, we aimed not only to meet our functional requirements, but to ensure that our product was simple to install and easy to manufacture in volume. To accomplish this, we designed our capacitive volume sensor as a single, integrated, flexible printed circuit board assembly. The sensor electrodes are integral to the Flex PCB and are backed with adhesives so they can be directly applied to the outside of the reagent reservoir, with control and measurement circuitry located on a rigidized tail. This integrated flex board can be readily fabricated and assembled at any number of manufacturers worldwide. Critical to the operation of our system is the measurement circuitry. After researching available solutions for digital capacitance measurement, we settled on 3 options: the FDC2214 and FDC1004 from TI, and the CTMU peripheral on a PIC microcontroller. We were drawn to the TI solutions as they're designed for the purpose and have compelling specifications. Initially, we selected the FDC2214 because it was the best on paper. However, complications during initial testing led us to switch to the FDC1004, which operates on a simpler principle. Our final design is based on the FDC1004 paired with a PIC32MK GP microcontroller.
To turn the design into reality, both open source and licensed design tools were used. The hardware and sensing electrodes were designed in Altium and manufactured by PCBWay. Before manufacturing, the electrodes were simulated in QuickField. The firmware was written in C using the MPLAB X IDE and the Harmony framework, which is specific to the PIC32 microcontroller used. The GUI was written in Python using PyQt. The electrode topology focuses on meeting the requirements of the high-resolution region while also being able to measure the rest of the tank. The high-resolution electrode uses an interconnected comb design that increases the capacitive response of liquid in this region. The design also accounts for environmental noise by including 2 reference electrodes, as well as shielding on the electrodes, the traces, all the way to the sensing unit. The combination of these features creates a design that is both precise and robust.
We used the QuickField software to determine the capacitance of the electrodes. The capacitance was estimated using the geometry of the electrodes, the voltage between them, and the electric permittivity of the material between them. To find the change in capacitance from empty to full, the electric permittivity in the simulation was changed from that of air to water. A change of about 21 and 35 picofarads were measured for the high and low resolution regions respectively. These values were feasible.
The firmware for our system was developed as 3 modules: acquisition, responsible for reading and scaling capacitance measurements from the FDC1004, algorithm, which converts capacitances to a liquid volume level, and interface, which controls the analog and digital outputs and reports a volume level over USB. The firmware makes use of the MPLAB Harmony Free framework, which simplifies our driver development. The majority of the firmware was developed on our prototype controller. This capacitive volume sensing project had been previously attempted with a similar approach to our own, so we wanted to make sure we caught any problems early on which couldn't be detected in analysis. To do so, we developed the prototype system around the time of PDR, which incorporated all 3 of our capacitive sensing options, as well as the rest of the circuitry for the device. This allowed us to begin on firmware development and testing early, and to evaluate all free sensing options to select the best one in practice. The electrodes were on their own flex PCB for the prototype, allowing us to iterate on them separately.
Wherever possible, I attempted to make 3D models of parts that we needed to order. Roche already had 3D drawings of the tank. Using the pre-existing drawings, I made 3D models of the tank, the cap, and the wire harness.
The capacitance to volume algorithm utilizes multiple capacitance values to calculate a liquid level. The reference electrodes are used to compensate for environmental noise in the tank or reagent. When the liquid level is in the low resolution range, the capacitance from the main and reference electrodes are used to calculate a volume. When the liquid level is in the high resolution range, all 4 capacitance readings are used to calculate the volume. This instills confidence in the readings when it is needed most. Each reagent has pre-calibrated reference values that accommodate the different dielectric constants. These reagent-specific values are loaded with the firmware.
We developed a PC-based graphical user interface for the capacitive volume sensor, which can be used to display and record the liquid volume level reported by the sensor's controller. Data is sent by the controller to the GUI over USB using a virtual COM port. When the GUI starts up, the user is prompted to select the COM port to read data from and the location to save files to. After the COM port is chosen, the user can start collecting data by clicking the Start button. Volume values sent by the controller will then be read and displayed by the GUI at a rate of 50 Hz. The current volume is displayed numerically and graphically as a visual representation of the level in the reagent reservoir. Clicking the Export Data button will export the data recorded since pressing Start to a CSV file for analysis and record keeping. The capacitive volume sensor GUI was written in Python using the PyQt library.
While we can't discuss exact figures, the design of our capacitive volume sensor enables a significant cost savings for Roche. The unit cost of our integrated flex sensor is approximately 1/4 of that of the original float sensors. This leads to an estimated cost savings of $300,000 a year.
The performance requirements were verified by comparing the volume inputted by micropipette and the volume reported by the GUI. The hardware interface requirements were verified using a multimeter, and the remaining were verified using the GUI. And the environmental requirements were verified using a temp chamber and a vibe table.
There were setbacks based on coronavirus that delayed shipping of hardware and stalled environmental testing. Initial testing shows that all interface requirements are met, and performance testing shows that at least the low resolution requirements can be met. However, ATP testing is still ongoing. We would like to thank our Roche team, Daniel O'Connor, Stephen Lay, and Nima Jamilpour for always supporting our team. In addition, we'd like to thank Mark Brazier for always telling us that we need to have a backup plan, as well as Gary Redford, Don Newman, and the whole senior design team for helping us get this project done.